Hello everyone, myself Priyanka Sharma. I'm a research assistant professor at the Department of Chemistry, Stony Brook University. Uh, it's nice to give a virtual talk at International Conference on Water Resources and Arid Environment, and I'm happy to be here. So our lab focus is on upcycling biomass waste for water purification, and during this talk, I will gonna talk about this subject. So before moving deep into my real research, I just want to give a brief introduction on the cellulose polymer that is the most abundant and sustainable polymer. So here is the examples of the plant biomass. The smallest unit in plant biomass is the plant cell, which is comprised of several components, including cell wall, and cell wall is basically comprised of the wood fibers. So these wood fibers are comprised of three major components that includes lignin, hemicellulose, and these are the cellulose fibers. Lignin and hemicellulose are not chemically resistant, and it can be soluble in many solvents, including water. Therefore, we don't want to utilize, or there is not a possibility to utilize this molecule for the water purification purposes, and hence we are more interested to work on this cellulose fibers. These cellulose fibers are basically multifibrillar structures that are interconnected by different hydrogen bondings, van der Waals forces. And if you see the chemical structure of these cellulose fiber, these are comprised of anhydroglucose units that are interconnected by 1,4 beta glycosidic bonds. So what's happened due to the complexity in the chemical structure, it is very, very hard or very difficult or intensive process to defibrillate these cellulose fibers. But our one of the focus of my research is extracting these cellulose fibers from different type of the plant biomass, or we can say plant biomass waste, and finding the suitable applications in benefits of society. So one of the application which I am focusing is on water purification. So if you see like because we have developed the nitro oxidation process where we can easily extract the nanocellulose from the untreated biomass. So what was the hypothesis behind this NOP process, that is nitro oxidation process? So when I checked all the things, and I'm thinking in the same direction that like for extracting the cellulose from these plant biomass, it needs multi-step processes, which include pre-treatment, chemical modification, defibrillation. So because of these multi-step things, the whole process become multi-steps and as well as expensive and non-sustainable. So the immediate question which came into my mind after seeing this is figure, that is it possible to combine all steps together? Because if we can combine all these steps together, then there will be definitely a reduction in the time as well as energy and water. So we started looking, or especially I started looking looking on the recipes by which I can reduce down the steps, and I can combine all the steps together to get the nanocellulose structure, or maybe functionalized cellulose. So this way we developed the nitro oxidation process, and we finally able to find a perfect recipe combined of nitric acid and sodium nitrite under a certain temperature and under certain time period, where we can directly convert this biomass directly into the nanocellulose structure. So this recipe is not allowing us to deal with the cellulose molecule, cellulose polymer only, but it's also removing the lignin and hemicellulose from the raw biomass structure. And also, not only this, this is also causing the chemical modification of the cellulose polymers. Here you can see that this nitric acid sodium nitrite cause the oxidation at the C6 position of the cellulose polymer and generates the carboxycellulose nanofibers. So initially our intention was to develop such a group on the cellulose polymer that can be helpful in the water purification. Means we wanted to have some groups that can cause the charge in cellulose fibers and able to interact with the positively charged impurities and can be helpful in the water purification application. And so this way we were able to get the perfect material for water purification application. And so as I said, like this NOP process or this recipe is not only working on cellulose polymer, but also helping to remove the lignin and hemicellulose component from the raw biomass. So the reason to use the sodium nitrite and nitric acid was one of the reasons to choose this recipe was because when I checked the structure of lignin and hemicellulose, all these components comprised of the primary hydroxyl group. And the chemistry of nitric acid and sodium nitrite says that it can generate the nitrogen dioxide as well as nitroxonium ion that can help to react with these primary hydroxyl group which are present in lignin unit as well as the hemicellulose unit. And once that react with these species nitrogen dioxide or nitroxonium ion, it can convert into the soluble byproducts. Like let's say here benzoquinone, here xylose and other directed products. So after doing this study on 16 different biomass waste sample, we were able to find that this process is highly efficient and can remove up to 95% of lignin from any type of biomass, as well as the 5% of hemicellulose. So these are all the theoretical mechanisms which we were able to find during this development, but the exact mechanism of reaction of this NOP process on lignin and hemicellulose is under investigation, and we are working on this as well. This is about the mechanism of nitro-oxidation process on cellulose that once nitric acid interacts with the sodium nitrite, it generates nitrous acid, and this nitrous acid in presence of nitroxonium ion generates the oxidizes the cellulose into finally into carboxyl group. So that we wanted to have, and so these are the hypotheses which we have used, and we worked and we finally found that these hypotheses on this recipe is working, and it's working on every type of biomass. So when we compared the process, our NOP process with the other conventional method, and we found that like through this NOP process or nitro oxidation process, we can directly get carboxylate cellulose nanofibers by only one step. While if someone wants to do the conventional pathway, want to use the conventional pathway such as tempo oxidation, carboxymethylation, then they have to go through several steps, which includes extraction and pre-treatment of cellulose, then bleaching, then like any chemical modification, then mechanical treatment, and then only they can end up with the carboxylate cellulose nanofibers. So you can see like we have actually transformed this multi-step into one steps, and that significantly saves the energy in terms of the water consumption, chemical consumption, and electrical energy consumption during the process of production of carboxylate cellulose nanofibers. Notably, the most important part of this process is that the recycling of the effluent during this process is very easy. Like this is the effluent, the yellow color effluent, which we get usually after the NOP reactions, and this is the recovered salt. So there is a very simple method to neutralize the salt, like just let this effluent interact with the some base. Here we have taken the example sodium hydroxide, and then you can end up with a salt that is highly rich in nitrogen salt. So we thought to utilize this salt in the form of the plant fertilizer, and we found that this salt worked very well, and you can see here the growth of grasses which took place in presence of this salt. So here this way we have followed a circular economy thing where we are using the biomass waste and using the effluent from the NOP process has a plant fertilizer. So although this process is using the acid for the production of NOCN, but we make sure that this process is environmentally safe, and that we did by using a closed reaction chamber. Like we are not allowing any case to leak out from the reactor, so that's one of the important thing. And so this shows that this process whole is highly sustainable and economic. So the all the development which I showed in the past slides are in phase one. Then during the development of phase one, we found some of the drawbacks from this process. That is the one of the drawback which I found was like the NOCN, the cellulose nanofiber suspension was not giving the gelation, and usually when we see the CNFs from the other conventional process like tampon, other, they give the gelation very quickly or at very low concentration, like let's say 0.28% or so. So that was one of the thing that was stuck to my mind. And then I thought the reason about this, and so I figured it out that maybe due to the low degree of polymerization of the product, and that may be causing because of the use of the high concentration of the nitric acid during this process. So I introduced two improvement. One was like the reduction of nitric acid concentration to 60%, and then also added the bicarbonate treatment, because initially the product which we were getting was in carboxyl form. So we wanted to have some charge on this fiber. So that's why we introduced the bicarbonate treatment, and finally we got a very good gel. You can see here like it's the NOCNF with 1 weight percent, and it is under a very average carboxylate group like 0.416 millimole per gram, it's giving a high gelation properties. So I would say this was one of the exciting moments that I had during this journey, and I was very, very excited to use this material further for the water purification purposes. And these are the properties, like you can see, these fibers are of very high aspect ratio, and these have very, once we convert this into nanopaper, it can have very high mechanical strength. So after looking on these properties, we were very sure that this is the material which we can utilize for the application of water purification, has an adsorbent, has a membrane, and this thing. So then, and these are the few examples that we extracted nanocellulose fibers from different agriculture residues. Like you can see, these are the fibers from sorghum stalk, maize stalk, bean stalk, millet stalk. So it is important to note that under the same reaction condition, all the agriculture residues can be converted into valuable NOCNF product. And by varying the change in the amount of sodium nitrite, we can also vary the charges on these fibers. So this way, we have successfully tested this NOP process on 16 plant biomass species, including phytosan. So we are now in the phase three, where we have set up the Scaleup reactor, and this reactor is designed by the Nocn, one of the Canadian company Nocn. We have also performed on this PHA, HAZOP analysis and SOP analysis. So we did some of the reaction on this thing, and we are just validating its capacity for the Scaleup production. And yeah, so everything is running smoothly currently, and that's a good sign. And so I started using this material for water purification by using this material to remove the metal and impurities. So here, one of the example which I have given here is the uranyl ions. We once it interact with the uranyl ions, the metal and impurities and the fibers get captured down, and these flock, we used to say it has a flock. So this flock can be easily removed by the simple gravity filtration process. So overall thing shows that this material, with the help of this material, we can really develop the cost effective method of filtration, and especially it is applicable to the places where there is a intense need of the of safe water. in advance, we have also tried the efficiency of dried NOCNF in the column filtration method, and it worked very well as well. With the this is, I think, with the arsenic impurities, we tried with the arsenic impurities, and we used this NOCNF suspension in the dialysis tube also, and we found that with the dialysis tube, it worked very well. So, and this way we tested this NOCNF for 8 metalline impurities, including lead, cadmium, copper, thallium, mercury, manganese, uranium, and etc. The important thing to note down is that this NOCNF has shown the highest efficiencies in most of the cases. And this is the higher than the existing adsorbent, bioadsorbent or chemical adsorbent, etc. So the reason then we try to find out the reason behind the highest adsorption capacity of NOCNF for these metal ion is that the mechanism involved during this remediation process is not only the adsorption thing. This nanocellulose also induce the mineralization of the metal ion during this remediation process. So that caused the higher efficiency of these NOCNF. So, and then we thought to solve the problem of rare earth metals, because rare earth metals are has very low abundance on that. That is only 0.023%, and day by day their demands are increasing, because we are continuously increasing the use of electronics, nuclear reactor, fuel cells, superconductor, nanoparticles, electroluminescent devices, and plastic fibers, etc. And also, like the mining of these lanthanum metal ions are very toxic to environment. As you can see in this photograph, this is about the mining area of the lanthanum mines in one of the area in China. And along with that, the whole world is facing with the water scarcity. So it is important to recover the lanthanums from the water, so that we can compensate the use of lanthanum on the earth, as well as we can save our environment by lowering down the mining of this lanthanum ion. So we use the NOCNF in this case also, and we found that adsorption capacity for our NOCNF was higher than 90%, and it again gave very high adsorption capacity. And as I said, this NOCNF not only involves the adsorption, but it also involves the mineralization of the metal that causes the higher efficiency of removal. And then we try to recover this lanthanum, and we use two methods, by acid treatment and by burning this the complex of lanthanum and NOCNF, and both give the good results. And by acid treatment, we were able to recover at 35% of lanthanum chloride, and in another case, we were able to recover, I think so, more than 95% of lanthanum oxide. So then we moved from the China to Africa, and we found in Africa, or whole world is facing with the fluoride problem also. So the reason to work on this fluoride problem is that because our institute is collaborating with the Turkana Basin Water Institute in Africa, and they sent us some of the water samples to test, and we found that in that water, the fluoride level was too high. So it was about above 14 ppm. And according to the US standards, the drinking water should have the fluoride level below 0.7 ppm. And the increase in the fluoride in water causes abnormalities in tooth enamel, joint pain, deformed limb and spine, and many other problems related to the bone. So, and you can see in this map, not only the Africa, not only the United States, but all over the world is facing with the fluoride problem. So we started looking for the solution for this fluoride problem as well. So what we did, because our NOCNF is comprised of the negative charge, because the method which we used is the NOP, and that creates the generation of the carboxyl or carboxylate group on the surface. But in order to get rid of this fluoride from the water, we wanted to generate some site like that has the positive charge. but it is not a simple chemistry because fluoride is a very small molecule. So to trap that fluoride, it's required to have very hard site on the material so that it can easily trap the fluoride impurities, or we can say should have the high positive charge. So what we did, we used the NOCNF and then we make a complex with the aluminum sulfate and did the fluoride remediation. And after making the complex with the aluminum sulfate, we found that aluminum is clearly bind with this NOCNF, and it creates the complex like this. And so with the fluoride solution, this aluminum trapped fluoride very easily. And you can see here, like when we put the fluoride solution into it, the fluoride and other impurities, the fluoride impurities settle down and the separated water is on the top. And so this again showed a very good adsorption capacity, and the process of making this complex is very simple and very cheap. So we are so optimistic that this can be easily applied to the off-grid community as well. So so then we found that this ammonium problem is again spreading all over the world, has a algal bloom. Like in the United States also, like 35 states are highly affected by the algal blooms, and especially during the summertime. So what this ammonium looks very simple, but it contaminates not only the land, but also it contaminates the water as well as the environment or air environment as well. So once this ammonium degrade by the bacteria, it's converted into nitrate and nitrite, and that finally converts into some nitrous acid and these type of species which goes in the water. So it's very important to capture this crazy ammonium. So and here we use only the simple chemistry because our NOCNF is negatively charged. So we thought to use to trap this ammonium from water, and we did, and it gave very nice result. So after having this ammonium and NOCNF complex or CNF complex, we thought this NOCNF is really acting as a good platform to capture this ammonium ion. So then we thought, like, why not to use this material as a fertilizer? So we sent back to the fertilizer, sent back to the soil as a fertilizer, and you can see these are the growth of the grasses which we found when we used this ammonium absorbed NOCNF in water. So this way, by using this NOCNF material, we have promoted actually the food, energy, water nexus cycles. We have cleaned land, air, and water. And in future, we want to apply this material to solve the algal blooms all around first locally all around the university, and then see what is the capability, like what is the real efficiency of this NOCNF. Then moved from the algal bloom, we come to the textile industries, because textile industries are basically fighting with the effluent, which contain high amount of the dyes. So NOCNF, so what we did, NOCNF, we simply used this NOCNF to treat the water, which is consist of positively charged dyes, and we found very good efficiency here. And then we also used this some modification to generate the positive charge in order to get remove the negatively charged dyes. And we found with this also it worked very nicely. Then we used some of the metal nanoparticles, and we generated in situ some of the nanoparticles to generate positive charge side and to remove the arsenic impurities. So with this method, we were able to decrease the secondary contamination, which happens generally when you only use the metal ion particles to treat water. And also with this substrate or with this novel inventions, we were able to recover this metal ion very easily. So with this, so our main focus, or what we can say, our main aim, or my main aim is with this research is to clean the earth, clean water, and clean air, and to provide clean environment for survival. So this research is mostly focused on upcycling the biomass waste for water purification applications and NOP method, which is highly cost-effective method to extract the nanocellulose, or we can say cellulose adsorbent from different plant biomass. And by using this strategy, NOP strategy, we can definitely promote the food, energy, water nexus cycle. Finally, I would like to acknowledge my mentors, my students, my colleagues, and whoever worked with me during this journey. Also, I would like to thank PSIPW for recognizing my work, Lavantnik Award for Young Scientists, and National Academy of Inventors for recognizing my work, NSF for funding, and different collaborating institutes. And this is our research group. And yeah, I hope you enjoyed my talk, and I'm willing to look for the questions. Thank you so much.